In this video, we'd like to discuss the differences between electric potential and electric potential energy, a topic that's come up in a couple of previous videos. So the first things first is that electric potential, of course, is this new electrical idea that we've been talking about that does actually have units of volts. So electric potential has units of volts, and it's a very electrical sounding concept, but as we mentioned in some previous videos, it is a difficult one. So we continue our sort of quest here to understand it a bit and maybe get some salient points out. And of course, electric potential energy, although it's also related to charges and things, it's just another type of energy. It actually is an energy and has units of joules. So what we're going to look at in this video here is just sort of a quick sort of contrast comparison between the two quantities. So what I have here is a parallel plate capacitor system. So imagine that this top plate's maybe a piece of metal plate. This is a metal plate also, and they've been connected to a 9-volt battery. Now in previous videos and things, the batteries are actually drawn like the square little box that they come in at the supermarket, but as you start to study electronics more, you'll realize that there's actually a schematic for batteries that looks something like this. The long terminal is always the positive terminal, and the shorter terminal is always the negative terminal. And in this case, we just label it 9 volts to indicate that we're connected to a 9-volt battery. Of course, when that happens, the positive terminal is connected to its respective plate, and a bunch of positive flow will flow out on that plate, a bunch of negative charge will flow out on that plate. So we have this to a certain point, of course, because the plates can become full, and there's our parallel plate capacitor system. And so what we'll do now in the capacitor system is we'll put a positive charge right down here. And we're going to put one positive charge over here, and we'll put another positive charge over here. But the charges that we're going to place here will have slightly different quantities here, or not even slightly, drastically different quantities. This one here is asking to be like a ball or something that's been charged to positive 10 nanocoulombs, for example. And this one right here, we'll keep it the very elementary charge here. We'll say that this one here is sort of the elementary charge of a positron or a proton, that it actually has 1.6 times 10 to the minus 19 coulombs on it. So we have two positive charges that have been charged to different charges, but they are both within the capacitor plates. And so what we know is that in the absence of any force, this positive charge will sort of stay stuck down to this negative plate, and this positive charge will do the same because opposite charges attract each other, and so the positive charges will be attracted to the negative plate, and in the absence of any neutralization or any special effects, they'll just sort of sit there like that. We can't do anything with them. But what we'll sort of imagine that we're going to do now between these two charges here is we're going to try and lift this one up, pick it up with our hands or however we can do it. We're going to try and lift this charge up and pull it all the way up to the positive plate. So this charge is going to be sort of lifted, physically moved up here like that. And we're going to do the same with this charge over here. We're going to lift them up and move them up towards the positive plate. Now the difference between the charges between being at the bottom and the top plate is that when they're at the top plate, they're actually storing a bunch of energy if they're held here, like pinched here with our fingers or pinched here with our fingers, because they're right next to a plate of the like charge, and they'd really like to get away from it. Like these positive charges in this plate would really like to repel this one down and away from it. So they're sort of being stuck there with some potential energy. There's your first indicator right there that there's something going on with potential energy, because they're storing energy, can be released. If I let go of this with my hand, the charge zings away and off it goes. So we'd really like to be down by the bottom plate here where it doesn't have any potential energy because it's just stuck to the bottom right there. So there's your first clue. But the other thing that happens now, at least that we're studying electricity, is this plate here can be sort of said to be at 0 volts because it's at the negative terminal of the battery. And if this is at 0 volts, we know it's a 9-volt battery, so this top plate must be at 9 volts. So in addition to these charges storing electric potential energy because they're near these like charges that we just discussed, they've also been elevated in electric potential to 9 volts. Because both of these charges here are stuck all the way up here near this 9-volt plate here, so we could say that each one of the charges is set at a voltage of 0 volts down here, but when we pick them up, they have a voltage of 9 volts up there. So there's a sort of bit of a contrast here. So we say they both have electric potential energy, yes, and they both have some voltage now, yes. They have both of these things. So what's the difference? What do we do with them? Well, it sort of looks like this. Let me get rid of these yeses here. Probably wasn't even such a good idea to write those in the first place. So anyway, what we have here then is that there is a key relationship here which says the change in potential energy of a charge is equal to its charge amount times its change in electric potential. This is the correlation between them. So we are talking about two different things here, but indeed there is a relation between them. It looks like this. So what we'll do then is let's just sort of examine what that is then. Let's look at the delta V's first. So for the 10 nanocoulomb charge, you notice that, well, it's gone from 0 volts all the way up to 9 volts. So it's experienced a delta V, this is our V's here, not U's, delta V of 9 volts. If you look at the other charge, sort of the 1.6 times 10 to the minus 19th coulomb charge, it also started at 0 volts down there at the lower plate and went up to 9 volts also. So it has also experienced a delta V of 9 volts. So this is something that's convenient about the electric potential that's actually measured in volts, that even though these two charges have differing amount of charge on them, one is at 10 nanocoulombs, one is at 1.6 times 10 to the minus 19th, they both have experienced the same change in electric potential, or their volts that they experience. And why shouldn't they? Down here they're at 0 volts, up here they're at 9 volts. That's all there is to say about it. But now if we start looking at the electric potential energy here, these are sort of like the delta V's that the charges have undergone. Let's start looking at the delta U's now, the electric potential energy. Well, we sort of have this relationship right here that sort of ties the two together. And so for the 10 nanocoulomb charge, the change in potential energy is 10 times 10 to the minus 9 coulombs. There's your nanocoulombs right there, or 10 nanocoulombs rather, times the 9 volt electric potential difference, or just potential difference that it went through. So the change in potential energy that this charge sort of incurs here by this motion, by moving up to that positive plate, is 9 times 10 to the minus 11 joules in energy, potential energy. So when I'm, let's see, this is the 10 nanocoulomb. When I'm holding this charge here and not letting it go, it's actually storing some potential energy of 9 times 10 to the minus 11 joules. And only when I let go can energy be released, say, in moving the charge. Okay? How about the other one? How about the 1.6 times 10 to the minus 19th coulomb charge? What sort of a change of potential energy does it incur? Well, the delta U here is going to be 1.6 times 10 to the minus 19th coulombs. And it also goes through a potential change of 9 volts. These are V's, not U's. So the change of potential energy of this charge right here, when it's sitting way up there, that top plate being held there, is 1.44 times 10 to the minus 18 joules. So there you go. And this is sort of the crux of the argument we're about to make here. So remember what's happening? Taking two charges, two differing charges. One at 10 nanocoulombs, one at 1.6 and 10 to the minus 19 coulombs. We're holding them near the lower plate of a charged parallel plate capacitor system. The voltage of the lower plate is 0. That's the electric potential, as is the electric potential energy. As we raise them up near this top plate here, they both sort of rise in electric potential to 9 volts. And they also store some potential energy, because if I'm holding them here, they're like buzzing with energy. They'd really like to release and sort of get away from that positive plate that I'm forcing it to be up against. And we've done some calculations here. Both charges, even though the charge amounts are different, have risen to 9 volts of charge. So they both have gone up to 9 volts. That's the change in their electric potential, not electric potential energy. 9 volts, same for both charge, and that's sort of interesting. But now down here, the electric potential energy that they store are drastically different numbers. One is 9 times 10 to the minus 11 joules. The other one is 1.44 times 10 to the minus 18 joules. So even though they've both gone up by 9 volts, the reason why their electric potential energy is different is, of course, because their charges are different. If you can imagine here, being in this electric field here, remember that F is equal to QE. So there's an electric field in this region here, and as I try and push these charges up against the electric field, this Q is a different number, so the one with more charge is actually harder to push up there than the one with less charge. That's why it has more potential energy stored in it by the time it makes it to the top plate. I had to do more work on it to get it up to that top plate. And lastly then, the difference between electric potential and electric potential energy are really in these numbers. So for electricity, we're usually not too concerned with the exact amount of energy a given charge stores, okay? Look at the numbers. They're very inconvenient. They have these big powers of 10 on them. Number of joules is 10 to the 11, 10 to the minus 18, and the 1.4. Who really cares about that? All we really care electrically is what voltage are these charges sitting at, and that's what's so convenient about electric potential. It's just a very clean number in volts like that, not these ugly numbers with the powers of 10 and the negative exponents and so on and so forth. And all we know about the charge is that they have some ability to do work or some electric potential because they're now up at 9 volts. We're not so concerned with the energy. So there's a bit of a contrast for you there between the electric potential and electric potential energy. And the real deal numerically anyway is just the numerics of them. A number like 9 volts, 10 volts, 100 volts, 120 volts, whatever the matter may be, are very convenient numbers for us to throw around, so that's why we stick with volts very much. These numbers here, although useful, are extremely inconvenient because of the powers and things involved. And notice also that differing charges can be brought to the same voltage even though the charges are different, but technically, yes, they do store differing amounts of potential energy because of their different charges. So that's just a bit of a contrast between the two things, electric potential and electric potential energy.